videos, and even things like three-dimensional point clouds. Now you might see a lot of these well-known applications and how successful they are when Facebook is like super creepily tagging your friends in the background when you didn't even know they were in the photo. There's Uber, who's driving their self-driving cars all around Pittsburgh these days. But it still, to this day, is so bad that it is the #1 way to tell if someone is a human or a computer. And that's kind of hard to wrap your head around because vision is something that comes so naturally to humans. But to get in the head of a computer, you have to realize what they're looking at, which is kind of just like an Excel spreadsheet of numbers. And you might be able to recognize what this is, because it's just zeros and 255s. It's a nice little smiley face. But you also probably can't tell what this random grid of numbers is, even though it's the exact same smiley face. So the next few slides, we're going to go over a bunch of different challenges that computer vision has to overcome. And I want you to try to think about what the actual pixel intensity values, how they might change based on each of these different things. The first one is scale and perspective, where you would have to recognize that the violin is a violin, even though there might be bigger or smaller ones, whereas in this picture on the bottom left, that's just a squirrel that's closer to you. It's not a giant squirrel attacking your mom and her minivan. The next one is occlusion, where you might be trying to identify something where you can't see something that's really important about it. There's viewpoint angle, where if you're standing to the left or the right of something, it might look like something completely different. There's local ambiguity, where if you just look at a small chunk of these images instead of the whole thing, you might try to peel this hose or throw that rock on your frying pan. Or you might miss out on a delicious piece of chocolate. There's within class variation, where you have to recognize all of these things as cars, even though they look completely different. And then there's also deformation, where something might take on a different form, even though it's the same object, which can be a life or death situation if you're not able to tell the difference between an Autobot and a Decepticon. And there's a whole bunch more, but despite all of these things, computer vision is still able to do pretty impressive things. And this is because of all of the research that's happening these days in the field. To talk about the research, we have to talk about the standard test data sets, where people can compare and see how well they're doing. The most common of this for the computer vision field is called ImageNet. Now, ImageNet is an absolutely brutal place where computer vision systems are pitted against each other in an algorithmic thunderdome of pictures of cats and stuff like that. The thing that it started out with was called the classification task. And this was just trying to identify one object where the whole picture is just that one thing. And in 2012, there was a resurgence of this algorithm called artificial neural networks, which we'll be talking about later. And because of that, they were able to get 85% accuracy on this challenge. And over the next 4 years, in 2016, they got all the way up to 97%. So high that they stopped even worrying about classification and started doing detection, where there's multiple objects and you have to identify where it actually is. And right off the bat, they were already at 66%. And things just kept going like that. And nowadays, we're doing segmentation, where you're doing a pixel by pixel level, identifying different objects, and it's all the way up at 81% accuracy. And the biggest reason for that is because people are starting to use artificial neural networks, the second topic of this talk. I'm sure a lot of you recognize the word neural, that this is related to the brain, but they are super different. Trying to compare the brain and an artificial neural network would be like trying to compare one of the best soccer players in the world and this guy. Or one of the best hockey players in the world and this guy. Or one of the best football players in the whole world and either of these guys. A neuron in the human brain is one of the most complex biological cells that exists. And an artificial neuron is so simple, I'm actually going to teach you how it works in the next 5 minutes. So an artificial neuron, a neural network, is what's called a graph in computer science. And this just means you have a set of nodes and a set of connections between those nodes. Those connections can have a weight associated with them and a direction associated with them. And in an artificial neural network, it is actually both weighted and directional. They're typically set up in a set of layers where you have a presynaptic layer, like this blue one, where it has feed-forward connections completely going to the postsynaptic layer, which is this hidden layer 2. One question that I get a lot is if this is like some hardware, physical, electrical thing, and no, this is all just AI, it's software, everything is in the computer. So now I'm going to teach you guys about a perceptron. And a perceptron is just a neural network that's composed of a single neuron, and its connections go directly to the input data. To keep it nice and simple, we're going to have the input data just be an x and a y coordinate, and we'll even keep it super simple and restrict the x and y to only be able to be 0 and 1. All that you have to do is you take your x, y point that your perceptron is trying to process, multiply it by the weights, a and b, add a constant, the c, and then you do some math, which we don't have to worry about how that works, and you get your output value. To keep it nice and simple again, we're just looking at these 4 points. And we might want to classify what's called the AND function, which just means we want the perceptron to output 1 if you're at the point 1, 1, where both x and y are 1, and you want to output 0 otherwise. To see how this works, we're going to take a look under the hood at this equation, ax plus by plus c. You might not recognize this equation, but I'm sure everybody remembers busting out their dope-ass TI-83 pluses in Algebra 1. Yeah, you guys know that shit. Equation for a line. If you remember anything else from Algebra 1, you know you can rearrange that to be that equation on top. So this is the equation for a line. And the only extra thing to know is if instead of setting it equal to 0, you set it equal to a value, you're basically saying things on one side of this line are a high number and things on the other side are a low number. So if you want to classify this AND function, you just got to pick A, B, and C, so you draw your line here, which means that neurons are a type of linear classifier. Now that's super fun that we can pick those values ourselves, but it's only important if it can learn this on its own. That's why it's called artificial intelligence. There's a lot of different ways that this works, but we're just gonna real quick talk about supervised learning, which is one of the simplest ones, where you basically just keep passing points into the perceptron over and over and over again, and every time you do it, you tell it what the correct answer is. So the first 3 points would say the correct answer is 0, and the last point would say the correct answer is 1. If the perceptron decides that it has an error, it changes A, B, and C. And if it doesn't have an error, it just leaves it the same. So using this, you can always put that line in the right place, or at least the optimal place. So what can a perceptron learn perfectly? Basically anything where you can draw a line to perfectly separate the data. But one thing that a lot of people have complained about with these perceptrons saying, oh, they're not that smart even though they're AI, is even with just these 4 points, you can't classify something as simple as the XOR function, even though there's still so little data. I don't know if we have any Silicon Valley fans out here, but this means this would be a very bad hot dog classifier. Unless you think that top left point should be this fucking monstrosity, in which case I'm not sure you're a human. So when you have more complex data that you can't separate with a simple line, you can still use artificial neural networks. Just now you have to use a whole network where they're all connected together. But the thing that's cool is every single one acts as a perceptron. So now that you guys all know how that works, you also know how these work. Basically, you just build a network, like the perceptron is a piece of Lego, and you're just building them together in different layers. So what happens is you get your input layer, which passes its value to the first layer. The output of that layer becomes the input for the next layer. The output of that layer becomes the input for the next layer. Not unlike the noble and majestic human centipede. And during the learning phase, it's very similar. You still have the output layer, calculate some error, and then every presynaptic neuron basically just takes responsibility for some portion of that error, and that's how it calculates its error. And then it's the same thing where the neuron has some error value, so it can update its weights accordingly. And it goes back until you get to the input layer in a system called backpropagation. So that's pretty much all you need to know. This is how artificial neural networks are doing these awesome things. But as humans, something you might be able to tell if you look really close about this bottom left task is that it's really fucking easy. Like, just, that's a dog. Anyone, like a 4-year-old child can do this. How are artificial neural networks so bad? And that is the question that made me take a jump from an undergrad in computer science to do a PhD in neuroscience. I wanted to learn what the human brain is doing that's so different. And the thing that jumped out at me the most was something that's not just like a biological explanation, but actually a biological function that is performing that isn't happening in these artificial nets. And it's the concept of active dendrites. I'm guessing everyone here knows about a neuron. You know they spike, which is kind of the decision-making capability of the neuron. If it spikes, it's happy. If it doesn't spike, it doesn't happy. But with an active dendrite, these dendrites will do their own additional nonlinear spiking mechanism. So in the 60s, when we first were inventing artificial neural networks, we thought that we just have to embody the soma, the cell body, and its spiking. But to actually encapsulate the full mathematical capability of a neuron, you also have to simulate these dendrites. So my research in school basically became how to do that. And something that jumped out at me was actually something that was invented at Carnegie Mellon in 1989 called cascade correlation. Now, the math behind this is kind of complicated, but it's actually really simple to explain if you just look at the pictures. So let's say we have a data set that's like this, where blue is bad and red is good. And I asked my brothers for a suggestion about what data might look like this, and they suggested I make my second poop joke of the evening. Should I shit here? The x-axis is the quantity of water. And the y-axis doesn't really matter. So with the perceptron, you can draw your one line. So you're not going to take a shit in a cup of water at a dinner table, and you will go in a toilet. But you'll also go in the pool. So that's So with cascade correlation, you basically have another node that is learning in the same manner, but instead of learning right versus wrong, red versus blue, good versus bad, it learns where its parent perceptron is already correct versus incorrect. And it's able to draw another line just like the linear classifier perceptron that is its parent. And then you add an output connection from it to its parent, and now you have two lines, and the parent not only knows the x and y coordinate that it already knew, but it also knows if it's the left or the right of this new line, making it a perfect dinner guest. The only extra thing to know is you can add as many of these cascade nodes as you want, and it sort of starts to resemble the biological soma and dendrites, at least as much as these guys. But the thing that's really cool about it is that it's basically just taking this core Lego building block and turning it into this more fancy one. So all of the artificial neural network research that's been done in the last 10 years, theoretically, is still applicable. You're just using a shinier Lego piece. So we put that to the test with another standard test beta set called MNIST, which is just handwritten digits, 0 through 9. We made a super simple network that just takes the image, the 29 by 29 pixels directly, passes it through 40 neurons, and then passes it to an output layer of 10 neurons, where the most active one is the decision of the network. The way that you train these things is you basically just pass the data set through it over and over and over again, letting it learn. And we did that until it went 10 iterations through the whole data set in a row where no improvements were made. And then we would add a set of these CC nodes to every single neuron, and then just basically repeat the process. And what ends up happening is after about 100 epochs, this thing flatlines at about 5.5% accuracy, and after adding all my CC nodes, it goes down to just under 4%. So we were super psyched that this thing works. But the best system in the world has convolutional layers, max pooling layers. It's got about 10,000 more neurons, 35 convolutional net voting committee data augmentation, making the thing way bigger. Its error rate is 0.23%, way the fuck off my chart entirely. So we had to see if it worked with some state-of-the-art stuff, and at the end of the day, it does, but not nearly as well. It makes it, the flat lines are where it went after adding CC nodes, and the dotted lines are basically what would have happened if we didn't. So it makes it about barely 1% better, but it's also about a zillion times slower. So we're not sure if it really has any value in the real world. But either way, it was fun. So, I hope you guys learned something from this talk. I hope you know that computer vision is getting better, but it still definitely needs a lot of work. And if you're gonna take something from it, I kinda wanna leave you with this. There's a lot of news that's coming out these days about AI and robotics, and a lot of them are just really sensationalized. Like, you have a lab that made one really cool video in a controlled setting and published it, and someone wrote an article about how we're gonna have robots tomorrow. And that's probably not gonna happen. And I personally feel like computer vision is one of the biggest roadblocks. The same way as you wouldn't want a blind person driving your car, you also don't want a computer vision system that's only 81% accurate. But I do think we're gonna see robots in our lifetime. And I also think in the next 50 years, we're probably going to get to a point where we can achieve humanity's real robotics goal of having robots do everything so we can just Netflix and chill all day.